So welcome to the next session of our lecture. Over the period, we are looking at solutions to first order differential equations. We've looked at the category or the class called separable equations. And we said that for a first order to be separable, you want to ensure that you can separate the variables involved. And from this teaser, we looked at an example where it was not separable, a prime minus 2b equal to x. This was not separable. And so the question is, can we not solve it, or what can be done about this? This leads us to the next category called homogeneous differential equations. Homogeneous first order differential equation. In this class, we want to make it separable. So it says reduce to separable. It is not separable, but then we can make it separable. And how do we do that? But before we do that, we'd like to know how to test for our first order being homogeneous or not. And so we want to first write a differential form. We've gone to the standard representation and differential representation. With the differential representation, we have mxy dy plus n of xy dx equal to 0. I could say that this differential equation of first order is homogeneous if I can find the same degree for the various coefficients. I would want to term that as homogeneous test. And so if I have a certain lambda x and then a lambda y, if I can represent this as lambda to the power n m of xy, as well as if I have the second coefficient lambda x and lambda y, I can also write it out or factorize the lambda out and have my coefficients. If these two lambda to the power n are equal, then I can say that my first order differential equation is homogeneous. Hence, I can make it separable. So let's take the first order. So it's homogeneous function of degree n. Let's take some examples. If I have a function f of xy is equal to x squared plus y squared, is this function homogeneous? If it is homogeneous, of what degree? So I just substitute my lambda x, lambda y. This will be equal to, wherever I see x, I have it as lambda x. So lambda x squared plus lambda y all squared. You realize that I can factorize lambda square out, or if I should expand this, I have this representation. With this, I can easily factorize lambda square out, giving me x squared plus y squared, which is also equal to lambda squared. This entire function is my f of xy. Hence, this expression is homogeneous with degree 2. The second example, it says indicate that or show that this function is homogeneous of degree 1. F of xy was given as 2x plus y. Is it homogeneous? Let's look at that. So lambda x, lambda y. Wherever I see x, I place the entire lambda x in plus lambda y. I can expand this, giving me 2 lambda x plus lambda y. You realize that I can only factorize lambda to the power 1 out and have 2x plus y. This equal to lambda, then my function is back. And so this is homogeneous of degree 1. These are simple functions. But in the case where a differential equation is actually given, so let me take a clean sheet. Look at the trial question here on the table. This is a first order differential equation given in the differential form. We want to test whether it is homogeneous or not. So this first coefficient here represents my m of xy. This coefficient represents my n of xy. So I take it step by step. M of lambda x lambda y will be equal to lambda square x square minus lambda square y square. This is equal to factorizing lambda square out, giving me x squared minus y squared. So that is degree 2. I take the second coefficient here. And that is just xy. So I have lambda x multiplying lambda y. If I should expand this, I have lambda square xy. And so if I'm comparing these two, I see that this is of degree 2, this is also of degree 2. Hence, the given differential equation is homogeneous of degree 2. Again, it means you can make it separable. Okay. The last example under this test, we have 2x plus 4y dx plus y minus x dy. Again, here is m of xy, and then here is n of xy. Let's see if it's indeed homogeneous. If I take the first aspect of the equation, lambda x lambda y will be equal to what? 2 of lambda x plus 4 of lambda y. Expand. Or I can easily just factorize lambda out, giving me 2x plus the 4y. What can we say here? This is homogeneous of degree 1 because the component here is 1. I take that of the n aspect, and so n of lambda x lambda y will be equal to lambda y minus lambda x. I can easily factorize my lambda out, giving me y minus x. And so this is also homogeneous of degree 1. Now, because they have the same degree, because they all have the same degree 1, it means that the differential equation given is what? Homogeneous. Until you're able to test for this, you can't really say it is separable or not. Right. So assuming all the equations we took are homogeneous, how then do we make it separable? Because we know how to solve separable first order equations. The rule is that first takes your separable form. The second is to integrate what you have. And then the third is solve for your unknown. We know these steps, and that is what we want to get at. But before we can make it separable, look at what we have from equation 6 to equation 9. These are the steps to make it separable. It says first, write a differential form, use some approach of differentiation, do a substitution, and then it can be reduced to separable. So I'll end for this session on the homogeneous test. And the next section, I'll take that of reducing it to separable.